Okay.
Hello, Doctor.
Hello. How's everybody?
Good, you look great.
Thanks.
Hmm.
So I apologize. I will be coughing quite a bit. So we'll see how far we go through the class today. Waiting for a few more people to join us. Let's see where we're at. So hi everyone. Again, sorry about lack of response this week since I've been under the weather. But I'm here. So, anyways, yeah, if you guys need more time for the assignment, I don't have a problem with it. Just you'll have other things coming up. Okay. Um,
Thank you.
yeah. And you can always schedule time to meet with me to go over a few things as
Mhm.
necessary. Let's start.
Do we need to ask for an extension, or is it just kind of
No, no. I mean, just I want you to get the stuff in and understand what you're doing.
Okay.
So, I mean, with the projects, that's a little bit different, right? That
Mhm.
I need projects on time. I mean, life happens and people get sick, obviously, as I am. Um, but really try to avoid that. Hold on, I'm starting my slides. Let's see. Here we go. Maricela. Oh, we got you. All right. So, again, I apologize if you've been reaching out to me. I couldn't even look at a screen most of the week, let alone do anything. But so I'm finally getting caught up on emails and stuff. And I'll be grading your discussions that you had last week, and posting the discussion for next week, over the weekend. But for the homework, if you need time, you need time. It's all good. I understand. I just want to make sure you understand what you're trying to do. And if you need help, I'm here to help. So this week, what we're going to be doing is talking about probability and confidence intervals, which is probably something you've seen confidence intervals on every paper you've read, right? But we have to do a little bit of probability first to understand how they're related. So first, what I'm gonna have you do is break out into groups, and I would like for you to talk amongst yourselves about project one. And I'll give you about 5 minutes to do this. And the whole point of this, that you don't have to write anything, but the whole point of it is just kind of go around. This is what I'm thinking. This is where I'm at. These are my concerns. And then we'll come back together. And I would like for you to have somebody in your group to share out like one exciting project, right? And one concern you have with the project. Okay. So some of these projects are like, oh, this one was really cool. So in the breakout rooms, I would like for you to have a team leader, that basically will share out for your group. And let's see how many is there here. Okay, this should work. So I'll join you. I'll open them up now. And again, just share amongst yourselves. And then say this one's a cool one. We'd like to share it with Dr. Hibden and everybody else in the class. And this is our concern for the project, or like one of the top concerns we had as a group. Okay. Questions? All right, I'm opening them up now.
I was on mute.
Hello.
Hi, I'm Chelsea.
My name is Anant.
Good to meet you, Nance.
Oh, you said that my name correctly the first time. Yeah,
Awesome.
perfect.
Hi, Maricela. Hi, Bonita.
Hello.
Oh.
Who wants to be the main talker back in the
I can take notes.
main classroom? Okay.
So whoever wants to start talking, talk, and I'll make note of it.
Okay. I think my main concern would be the data.
Yeah.
I think that's the main purpose of this class.
Mhm.
So I just want to make sure I have the best understanding of the data.
Yeah. What's your
from the research.
What's your
And there's actually no RStudio or Excel use in the first part of the project. I think that comes in project 2. Part 2.
What's your topic?
Contraceptives.
Okay.
And I'm actually getting firsthand research through Student Health Services through a survey. So I'll be using my own original data collected throughout October.
Awesome. First time users of contraceptives. Wow. That's exciting.
Yeah, because we have those health vending machines on campus with the Plan B and the male and female contraceptives.
Yeah. I don't know if I have a good understanding of what the project is.
Yeah, I'm looking at the PDF now for that.
I think we're supposed to find a public health issue topic, right?
Yeah, I got that.
Yes. And it's the literature review.
Okay. Oh.
And the presentation of data within the literature review.
Okay. Okay.
Is
Wow.
that on?
Feature analysis and limitations. We did some of those limitation exercises for the homework. So we have some practice with that. So that's good.
All right, go ahead, Marcella.
Oh, I was thinking about like just exploring maybe the topic or the public health issue, childhood obesity. So that's what I was looking into. As far as any issues or challenges, I think the whole experience is a challenge. So overall, I don't really have a main issue or a main concern at this moment. It's just basically just kind of doing research and, looking at similar data, just trying to learn, read the chapters basically to just get a better understanding.
Yeah.
So that's what I'm really going to focus on at this moment. But I don't really have any concerns besides just learning.
Yeah. I'm doing tuberculosis in the US. My issue is I really want to narrow it down because that's such a huge topic. Like, I don't know if I want to address follow-up treatment for recent immigrants and refugees who come in to the United States and how that's working, or I'm kind of just because that's a hot button issue right now. And, and also I'm struggling deciding how to narrow it down because I don't know if I want to do that or complications with COVID, but I don't know if there's enough data. So, yeah.
For mine,
yeah, go ahead.
For mine, I've decided to narrow it down contraceptives to college students and young adults.
Yeah. It's first time users of contraceptives or first time users of the machine or the whatever's on campus.
Whatever's on campus, and the research will be all
young adults,
college age students contraceptives.
That is so cool.
Like Plan B, condoms, that stuff. Yeah.
Yeah.
That really does make me think about like how if I should narrow it down more to like the United or high schools maybe, or targeting, because it's gonna be a lot of information. I don't want to get lost or just frustrated.
I think the way to figure that out is like my concentration is in health education, so mine will be a younger population. But if you're more interested in geriatric, or if that's where you want to be at a job, it's like focus on the older population.
Right.
So make it more relatable for you.
Right. Okay. That's a good way of thinking about it.
Yeah. Or just look at and see have you started doing the research and where the most data is?
No.
Yeah, I got it from the library EBSCO host.
Yeah. What about you, Marcella?
No, not yet. I'm going to though.
Yeah. Because it'd be interesting, like early childhood versus adolescent. Right. Yeah.
Okay.
Oh, I'm sure people have tracked like obesity rates, like 5 and under, and then follow up.
All right, welcome back. Why don't we start with Ivory, Kelly, and Tiara? Who's from your group is sharing out?
I guess I am. Um, I feel that we all have good topics. Um, Kelly topic was on homeless veterans and suicide rates. Mine's is on postpartum breastfeeding, and then Tiara's. I forgot what yours was. I can't hear you, Tiara.
Mine was on like how the access of prenatal care affects perinatal infections.
Oh, wow.
Yeah,
Yes.
and some of our concerns were like the topic not being broad enough, so not finding enough data. If we narrow it down to like just the Chicagoland area or maybe even like the United States, basically, and then being able to find like really good charts as well on it, because I know we're not creating ours from scratch. So yeah.
All right. How about Alexis, Bonita, Hiba, Yana, and Zahara? And if I'm butchering people's names, you can let me know. Who's your? Yeah, go ahead.
Anybody passionate about presenting? Hiba and Bonita have a similar topic. They're looking at oral health. Correct me if I'm wrong, Bonita, but you wanted to now focus, kind of expand on your capstone, focusing on oral health, comparing United States and other countries, and see how those compare. And are you looking at just the Black community or all demographics?
Most likely the Black community, and I'll keep it I'll keep it a little bit broad, just because I know other parts of the world don't have what we call African Americans. I think that only exists in the United States. So yeah, Black communities.
Yeah, that would be interesting to look at how, I mean, I guess defining it as Black, how Black oral health compares to between US and England, for example, how Black oral health is there and how, is it better? Is oral health for Black individuals better there or in the United States? And then Hiba is looking at oral health between Blacks and whites. And I think you said you're focusing on the United States, right, Hiba?
Yeah, within US, I'm looking for the disparities. Also, like in disparities, considering cavities, like how many people are having cavities, or what is the tooth life among both of the race, and oral cancer, like that.
That's great.
And then I will also like to expand. I did a data analysis for my capstone, but I utilize Excel, and maybe I'll utilize R, and in a more now that we have the entire semester to do it, I feel like I will be able to go more in depth, focusing on maternal and infant health, probably just in Chicago, looking at different zip codes. That COVID paper gave me a good idea about looking at how is there a difference in maternal and infant health or even mortality from Rogers Park down to the south side or even the west side. So that paper gave me a good idea about what I wanted to focus on.
That's great.
I'm sorry, can I jump in and say something about what Yana just said? Because I was in Yana's capstone class. Yana, you can't do that. You can't, because she did an amazing job doing like a statistical representation of infant mortality in different parts of the United States. I thought it was so cool. You guys would be missing like a huge part of that if she only presents for Chicago. Sorry, Yana, I had to put that in there.
I'm Benita and I are pretty passionate about our topics. I know they always say like, add some variety to your classes, do different things. But we're both pretty passionate about the topics we've chosen, and maybe we'll take a different perspective on how to approach the topic and be able to present it differently. But yeah, I mean, if I could, delve into it again differently in this class, I would love to continue it.
Yeah.
And then was there a common concern that you all had about the project?
The same thing with Ivory's team. We were concerned about the amount of information, the amount of data we'll be able to find. And so we hope that, especially for HEBA's one, I believe it's specific. And so we hope that we can find specific enough data for her to utilize for her study.
Yeah, I agree. All right, and Ananth, Chelsea, and Maricela.
Is it okay if I share?
Oh, yes, please.
Okay. I took notes, but I didn't ask the group if I could talk. Kind of really cool projects. Ananth is working on contraceptive use among college-age students. Particularly, he's collecting data on campus. I guess there's vending machines for contraception there, and so he's actually using that data, which is kind of awesome. And then Marcella is going to be studying childhood obesity. I'm going to be doing tuberculosis in the United States, and I'm thinking about doing it among recent immigrants and refugees, especially with follow-up treatment and latent TB. Concern about data that Marcella and I had in particular is kind of narrowing it down a little bit. Both our topics are fairly big, and we need to sort of zoom in on an issue. We all were concerned about this is such a new way of looking at this data, and it's going to be challenging for us, but we're all very excited.
Yeah. So so this is great, and thank you so much, everybody, for talking out. And I know it's always hard on Zoom. I love the topics that I got to hear about. I'm excited to learn. Like reading your guys' projects, I get to learn so much. And you're gonna be sorry, I have a cat, and so you're gonna hear some stuff in the background. So I think that's important in terms of the data. So one of the things I want to caution you against. So some of you will have a lot of data and you'll have this giant table or something like that. Do not insert the giant table. Why? Because you don't really need all the information in that table. What do you want to direct the eye to? Remember, you are telling a story. Your job is to tell the story and to show me the data that's relevant towards the story you want to tell. What I mean by that is you might have data that is, so we were talking about oral health for Black people versus the US versus the UK, I think was the, right? What you're going to have these tables that are huge. The problem is you might only want to focus on one piece of that table. So you can say the amount of times going to see a dentist, right, in the US, but that whole table might have seeing a dentist, having dental insurance, having oral surgeon, blah, blah, like all this information. You're like, but you don't. That's not the story you might be telling, right? So make sure you can cut and crop a table, or you can create the table yourself. You can take the piece of information out of the table and create it yourself. In terms of the figures, make sure that they're clean figures, and you have to reference the paper that you got the figure from. Okay, those are very, very important pieces. I understand project one is for you to learn, and I will be giving you a ton of feedback on that first project to guide you to make sure that you have a better project. You have a better project 2 and project 3. Okay. So questions about the project? No. Okay. I think you all are going to do great. I'm so excited. So I don't know why, but I am. All right. We'll talk about the paper when I need a break from my voice. So let's talk about probability. All right. Let's see. So what is probability? I personally think, oh yes, Zahara.
I wanted to ask about today. Can we submit an Excel sheet with our assignment to paper, like the Word document?
Yeah, I would love that. Yes, I would love that.
Okay.
And one of the things
I have both.
Yeah.
I
One of the things
I kind of did the work in the Excel sheet and then like answered on the paper, and then I did provide the figures in the actual Word document, but also the work in the Excel.
Oh, that's awesome. Yeah, I'm excited to see how you do it in Excel. Yes.
Okay, cool. Thank you.
All right. So thank you for asking that. All right. So probability, I think of games. I can't help myself. I think of games. um, yeah.
Yeah.
Sorry, I'm on mute. And so let's talk about it more because why is it important to us? So the probability is like the likelihoods that something will occur. So what's the likelihood that you're going to go to sleep at 9:30 tonight? Nobody's going to throw out something? I probably will. If we make it to 9 tonight, I'll be surprised. What's the probability that you will wake up at 6 a.m.? These are foolish examples, but that's how probability works. So the whole important point of this is that probability theory is what guides our ability to do statistical inference. And the goal of this course is to do statistical inference. Take data, infer some information from it, and try to understand what has happened. So, well, recall you can't survey a whole population. You're only surveying a subset of the population. So you can think about it as a portion of the population. And here I've given some notation that we talked about last time in class. I do want to recognize that we use Greek letters for the population, mean, and standard deviation. And then we use like standard deviation is S, sample mean is Y bar, sample proportion is P hat. Proportion is saying a proportion of the population. So, what portion of this class identifies as female? What portion of this class doesn't? So what happens is what we do is we have to do what's called probability sampling. And what that means is we have a known probability of a selection happening. However, there are times when we have to do non-probability sampling, and that means we're taking a selection from the population without using probability. I don't think this is too important. I have it here because it's something that I personally have to wrap my head around, but we might come back to this later. So we talked about last time is simple random sampling. Let's say you have a total population of 15 for this course. I get all of your social security numbers or all your student ID numbers, and I randomly pick one. Well, the probability of you being chosen is 1/15. Systematic sampling is I'm going to choose. Do you ever remember playing a game where you're like counted off 1, 2, 3, 1, 2, 3, 1, 2, 3? Or you're in a classroom where you have to do this and then you group off based off of that. That's selection based or systematic sampling. And then finally, stratified sampling. So what you do is you take the population, you say people that are in higher education versus not higher education, city versus not city. So I take the population, I divide it up in these two categories or stratification, and then I pull them. Another example is you can say people who work full-time and don't work full-time. That's a good example. First generation, non-first generation, migrants versus non-migrants. So you're basically taking the population you're trying to work with and you're dividing it up. This is pretty well known. For non-probability sampling, it's just the processes are pretty self-explanatory. Convenience. Oh, hey, you're all in my class. I'm gonna sample all of you and see what happens. Quota sampling, it'll never come up. So, but how do we calculate probability? So what we say is the probability of an event occurring. So my favorite thing I always tell students is me going to the moon. Probably will never happen. But we know that's between 0 and 1, right? And it gets closer to 0 as I age. But so the probability is always between 0 and 1. And this is like an important piece that people mess up all the time. They're like, what's the probability that you have the same birthday as mine? It's like, it's 1 out of 365. By the way, it's not true, but that's okay. How do we calculate probability in general? Calculating probability can be quite complicated. I actually struggled with it a lot when I took a probability and stats course. I really struggled with calculating probability because in some sense, it's very simple. You take the number of events that's going to occur, right? But divided by the total number of events. So what do I mean by that? So the number of events, let's say we roll a die, right? What's the chance of getting a 6? So the total number of events is 1, 2, 3, 4, 5, 6. But the number of events of rolling a 6 is only 1. So it's 1 out of 6. It becomes more complicated if you add more die. And this is not the point of the course, is be able to calculate all these probabilities, but to understand like some of the basic stuff. Let's say what's the probability of picking someone over 30? I have oh yes, Yana, please.
So the example with the die, it seems pretty easy because you have a set, it's like it's a concrete number. But then like the example that you had was the probability of you becoming an astronaut. There's no like concrete like denominator to figure out. Like, would you then look at the number of men your age who are astronauts?
Yeah, pretty much.
And then it'd be like 1 over those number of men.
Yeah, that's how you would do it. Yes, basically. That's why it'd be 0. There's no astronauts above this age. I'm not giving my age, dang it. But yeah, that's how you would try to do it. And again, a lot of times it's calculating probability is like really kind of I kind of find it the one magic piece of math that I always struggled with. But let's say that I have a total of 22 students between all my courses, which I do. And so what's the probability of picking someone over 30? Right? So I want to pick somebody from my class. I'm going to randomly pick one of you from this class and my other course. And the question is, what's the probability that that person's over 30? Now, I don't know all of your ages. So but it could be 11 out of 22 or 50. Let's say there's 11 people in the class that are over this course and my other course that are over 30. Well, the chance is 11 out of 22. Or if there's 15, it's 15 out of 22. So you have to actually really know the population you're working with, right? People always use deck of cards, right? And if we were meeting when I used to teach this in person, we'd have a deck of cards and we'd play a game. But I can't do that, right? But what's the probability of drawing a spade from a deck of cards? Well, there's 52 cards in a deck, and there's 13 spades, so it's 13 out of 52, or a quarter. Probably getting someone who works in the medical field out of all of my students. Well, I don't know what all of your jobs are. I actually know from my other class. So let's say there's 16 of you. So it'd be 16 out of 22. Or if there's 4 of you, there's 4 out of 22. So again, you have to know the population or what you're working with to be able to calculate this stuff. And that's why I always struggle with it. And I have this big in red, and I think this is very important, is this really getting us to false positive and false negative. So has anybody seen false positive, false negative in any of their studies or any of their other courses, or heard it anywhere in their lives? I want to speak up or put in the chat. Yeah, Yana. Go ahead. You're muted. It's okay.
Test results can be sometimes false positive or false negative, and that's where I hear it from usually.
Yeah. Anybody else?
Yeah, I had a false negative pregnancy test.
And that happens a lot.
Yeah.
This- yes, that is a very, very common. That's why you do it multiple times and go to a doctor and get a blood test. It's less likely. But yeah, I'm avoiding telling a story. So how is this calculated? So remember, these are probabilities, right? So we have what's sensitivity, which is, let's say, the probability of the disease. Let's say I have the disease and I screen positive for the disease. Okay. Specificity, I cannot say that word ever, is I have the probability of the probability that I am disease free, I don't have the disease, and I screen negative for it. So sensitivity says the probability that you have the disease, I've chosen somebody with the disease and they screen positive. I've chosen somebody that's disease free and they screen negative. A false positive is 1 minus specificity. Specificity. Oh my God. I'm glad my wife isn't here. She'd be laughing at me. And false negative basically is 1 minus the sensitivity. So let's talk about false negative. What that was saying is basically I've chosen somebody that they do have the disease and they screen positive. But a false negative says, it's 1 minus that. So what that's saying is you've tested negative, but you actually have it, right? So again, this occurs a lot. And when you're reading it in papers, like, oh, this is the amount of people that had false negative tests is the following. They should, and they won't, put it in a percentage. It's a probability. It's always related to a probability. Okay, so what's the probability? And I remember actually asking a doctor once about the pregnancy, about having a false positive and over-the-counter pregnancy test, and some have them on. And we love the doctor, but they couldn't explain it all, and it took me, a few weeks to try to understand online. So these questions, people don't explain it well. So they're understanding the difference between being false positive and false negative. Okay. So how does this work? So what we think about is we have positive predictive values. And so what this is saying, a positive predictive value, right? Oops, sorry. I don't want you to be scared by the calculations and everything like that, because we won't be doing too much of it. But this says the possibility or the probability that you have a disease and you screen positive. The negative predictive values is the probability that you are disease-free and you screen negative. Okay? So how do these probability rules work? So what happens is probability value between 0 and 1, as we always talked about. If anybody gives you a probability value bigger than 1, they're full of baloney. Okay? The sum of all the events does sum up to 1. So what does that mean? The probability of me going to the moon and not going to the moon is 100%. I'm either going or I'm not. The probability of you going to sleep at 9 versus you not, or 9:30 versus not at 9:30 is 100%. Right? You either are or not. So the sum of those events together is 1. The probability of getting a spade, getting a heart, getting a diamond, getting a club, and a deck of 52 cards is 1 out of 4, 1 out of 4, 1 out of 4, and 1 out of 4. So that's 1. Excuse me. And then finally, the probability that event will not happen. Well, let's say the probability that I will not, that you will not go to sleep at 9:30, right? So going to sleep at 9:30 is that E. The probability of not going to sleep at 9:30 is that E to the C. So let's say the probability of you going to sleep at 9:30, 10%. The probability that you're not going to sleep at 9:30 is 90%. Why? The sum has to be 1. Okay. So what does this mean? And again, a lot of this, we're just setting ourselves up. I just want you to recognize I'll be doing a lot of the calculations for you. But this is actually here is very important. And what we have here is I have Venn diagrams. On the left, we have a disjoint or independent events. So event 1 and event 2. And you can say, what's the probability of me going to sleep at 9:30? And what's the probability of me going out this weekend? In general, they're probably not connected. They're probably independent of each other, right? Maybe. So we say those two events are independent of each other. They don't depend on each other. And we can calculate the probability of going to bed or going out this weekend by just summing the probabilities. However, if it's an intersection, that means, let's say we say, actually, to be honest, if I don't get enough sleep on Thursday night, I know I'm not going to be doing anything over the weekend. And so there is some overlap, right? And so in this case, we say that, well, some of the times, if I go to sleep at 9:30, or I go out, well, some of the times there might be an overlap that both won't occur or both will occur. And this is known as this intersection. And this means that there is some dependency on the two events. And you can imagine this is actually even more relevant when we talk about a drug, right? So what type of drug should I give you? Well, the drug should be given to you, right? Such that you're not taking another drug, right? There's certain drugs interact with each other. So again, this is the calculation. I won't worry about it too much. We'll do some examples here, but again, it's not meant to blow your brain too much. I don't want to, but I'm a mathematician. I have to have my formulas. So I apologize in advance. And you will have reference to all this. So let's think about an example of hair color and eye color. Is hair color and eye color independent or this intersection?
Independent.
Why?
They both are different things. In terms of color,
independent because they are from different genes. The genes for the eye color and the genes for the hair is different.
Okay. And is that what you're kind of heading towards, Eva?
in that way, it's also same. But I think like if someone who doesn't belong from medical side will think like they both are separate things.
Mm-hmm.
Okay. Okay, I like that. Yeah. And to be honest, sometimes when you have to try to answer that question, the real question is, do I have enough information or do I have to reach out to an expert to explain it to me, right?
Mm.
It's okay. Like the gene is actually the perfect answer, but it's okay for us to go, are they? Right?
Right.
Right. And then you're like, well, maybe I should ask a biologist.
Mm-hmm.
Because I'm not an expert in that area. Never be afraid to ask an expert. It is not expected for us to be experts. But yes, I do like your example. Okay. So in this case, they don't depend on each other, but let's say one event depends on another. So excuse me, sorry. So what we have is the probability that I'll get 8 hours of sleep tonight, or the probability that I'll go to bed at 9:30, given the probability that I will get 8 hours of sleep tonight, given that I go to bed at 8:30 or 9:30 tonight. Right? They actually depend on each other. You know they do, right? Your timing of when you go to bed, unless you're very lucky, really dictates how many hours of sleep a night you get. Okay. So what we would say is the probability that I will get 8 hours of sleep is E2, given that I went to bed at 9:30. So we say the probability of getting 8 hours and going to bed at 9:30. So I'd have to understand my body, right? And how many times does that happen? Divide by the probability that I actually go to bed at 9:30 on average. I should have surveyed you all before class today and asked you how many of you go to bed at 9:30. I could have done some of these fun calculations with this. So if two events are independent, we say, what's the probability? Black hair and blue eyes. Right? They're independent. Okay, I'm black hair, blue eyes. So I'm being selfish. And so you'd have to like survey a large population to see what is that probability. And if the two events are dependent, right? 8 hours and going to bed at 9:30. Basically, this is a reverse calculation from the previous slide. Just bring this over. This is cheating. The same calculations. All right. So what we're going to do is I did these calculations. This is from example 1 in the book. And what we have is we have a table. When I converted this to PowerPoint, these got cut off. This is what happens when I'm sick. I don't get to look at my slides well, so I apologize. So what we have here is we have low income, medium income, and high income of a surveyed population. And we surveyed if they smoke or don't smoke. There's a caveat here. You're assuming people are truthful about that information. Are people truthful when they respond to surveys? Yeah, I actually don't know. It's a question I ask every time I teach this course. I'm waiting for somebody to find a good study on it. I haven't found one. I know there's one out there. I just haven't spent the time doing it. So a question is, what's the probability that someone in the study is from low income, right, and smokes? So what's the probability if I choose from this whole population that we're going to get somebody that's low income and smokes? And my question to you all, are the events independent or dependent? Yeah.
I think they're independent. And are you asking answers for both questions?
No, I was just curious if independent or dependent. But yeah, go ahead. Lead us how you would calculate it a little bit.
I think it would be 634 over 6,549.
Yeah, can you tell us guide us how you got that?
I'm trying to think of how I did that myself. Because you said who are low income and smoking. That's just a small portion of the entire population of people, of smokers, non-smokers. And that's why I don't know. I'm not sure how to articulate how I.
That's okay. No, it's okay. You did a good job. Yeah.
And
yeah, go ahead.
Taking that larger number of 6,549 sort of limit the assumption that people on the lower income have a high, it reduces the bias that people who have come from low income status smoke more. Like, for example, if you use the total, the 2,480, that would kind of be biased because it'd be a higher probability, or no?
That's a good question. We will have to answer that. We have tests to figure that out. And
Okay.
You're jumping like 3 chapters on me, and I love it.
Thank you for being.
Yeah, no, that's a great question. We have a way to test if there's an issue with that.
Okay.
So, by the way, the best way I used the calculation here from the formulas I gave, but to be honest, just take the 634 that we have. And let me see, hold on. I think there's a way.
Professor, I think I was thinking for that one, if you put everyone in a hat, like all 6,549 people, and you put your hand in the hat, the likelihood that you would get someone like who's low income and smoke is 634. Maybe that's.
Yes. I'm trying to do something and it's not letting me. Yeah, it's basically, that is correct.
That is a really helpful way for me to think about it. Thank you, Yana.
All right. Next question. What is the probability that someone in the study is not from low income? Many ways to do this.
I mean, I would say, oh, sorry.
No, you're fine. Go ahead, please, Benita.
Okay. I would say, I mean, basically just sort of like in line with Yana's explanation. Just the low income don't smoke out of like the total number. Or I get whatever value that I get from low income smoke out of the total minus the total number of low income people, which I think that might be a little bit more complicated.
You're on the right track, actually. I think the key here is we don't care if they smoke or don't. What we just want is the total, right? But you know the total amount of low income, correct?
Right.
You know what you could do is probably just add the medium and high and divide by the 6,549, right? Because that's the total. There's another way. We just take 1 minus that 2,480. So there's many ways to do these calculations. But I'm trying to use the formulas a little bit. Yeah, if we were looking for low income and smoke. What is the probability somebody is from the low income or from the medium income? Are the events disjoint? Can you be from both groups? Can you? Why not? Well, yes or no? Why?
No.
Why?
Because the low income are pretty much in that category, and you can't be low income and medium income at the same time.
Yeah.
But
yeah, they're independent. Yeah, I agree. Go ahead, Kelly. What's up?
Oh, I thought you were combining the low and medium groups, though. So that would be one group if you said the chances of someone being from the low or medium.
Yeah. Yeah, go ahead. Sorry.
I figured you're combining that into one group, the low medium group.
We're going to, but to do the calculation, we have to understand, are they disjointed or not, right? Is there an overlap? Correct? Think about the Venn diagrams. So you have low income and medium income. If there's an overlap, we have a different calculation than if there's not an overlap. That's the important piece. But you're correct. So to be from low income or medium income, just you sum up. What's the probability of being from a low income, medium income, or high income?
1.
100%.
Yeah,
One. Yeah.
Yeah, 100%. That's right. I mean, it sounds like a trick question, but people actually struggle with this to understand that if all my population's in these 3 categories, if I say what's the probability of being in one of the 3, it has to be 100%. All right. So what we're going to do now is take our first break. Actually, hold on. Do you guys mind if we take a little break now?
No, I don't.
I need to get some more water for my throat, so I apologize.
No worries.
All right. Can we get back here at 7:07?
Mm-hmm.
You're all thinking I'm weird. I'm a
Yes.
weird odd number. Hey everyone, welcome back.
Hey, Professor, could I ask you one quick question about
Go
the
ahead, Kelly.
probability thing?
Yeah.
So is it that you can only figure out the probability of a particular thing, a particular outcome, if you know what all the other possible outcomes would be?
Not necessarily. What if I know what all the outcomes it's not going to be?
So you can rule out everything else.
Yeah, and then I do 1 minus that.
Okay.
That's and to be honest, Kelly, this is where I actually struggled with probability. You think mathematicians are great at this? Generally, they are. I'm just a weird duck, and that's okay. I've accepted this, and I always struggle with probability.
At least I know I'm in the right ballpark if it's a valid question, though. So,
Oh, it
okay.
is a very good question, because you can imagine from a health perspective, it is a problem, right? But again, our goal here is this is helping us set up to be able to do a little bit more interesting calculations, right? Because remember, probability is because you're sampling a population. So it's a great question. Great question. All right, I hope everybody's back. I'm gonna share my screen. Okay. I thought I was done with the coughing. So why is this important? So what I want to talk about is binomial distribution. What a binomial basically means, it either happens or it doesn't. And again, you don't have to worry about these formulas. You can, and you're welcome to. There's ways to do it without, but I can't help myself. I will never forgive myself if I didn't have the actual formulas. And some of you probably love it, which yay. I'll slowly convert you all to the dark side to enjoy seeing complicated formulas. But basically a binomial means bi, right? Two. Nomial means options, basically. So you have two options. Either it happens or it doesn't, right? So you roll a die. What's the probability that you're going to get a 6? It's 1 out of 6. It either happens or it doesn't, correct? But let's say, what's the probability that I roll a die 9 times, right? And I get a 6. 6 times out of that. Sorry, my notes, again, I didn't get a chance to, I write stuff up and then I edit, and I haven't had a chance because of being sick. So this is kind of what that calculation is. It's saying we are going to roll the die 9 times. We know that the probability here, P, is 1 out of 6. And we want to get a 6 times. So it's 1 out of 6 to the 6th power. The probability that you don't roll a 6 is 5 out of 6. Okay. And the probability is 9 minus 6, right? I mean, the amount of times you don't get it is 9 minus 6. These exclamation points are actually called factorials. If you want to be able to calculate this by hand, please come talk to me. Okay. But I don't want you to worry about it too much. But I can teach you factorials like that. I love factorials. So what I would like to do is problem 1 from chapter 5 of the practice problems. And what we have here is hyperlipidemia occurs 30% in children 6 to 12. The question is, if 12 children are analyzed, and we want to know exactly when we will have 3 with hyperlipidemia, sorry. So what we say is, right, you either have hyperlipidemia or you don't. There's no middle ground. You either have COVID or you don't. You either, right, you have a pneumonia or you don't. So what we say is, what's the probability that we'll get 3 children with hyperlipidemia out of 12? So I take 12 children from a classroom, and I want to know what's the likelihood that they will have 3 will have hyperlipidemia, and it's about 23% or 24%. Well, why is that important? Let's say I do this in a classroom, and I get 50% of the 12 children have hyperlipidemia. I'm like, oh, that's weird. I'm like, well, maybe I have to do it with a different set of the population. All right. I choose another classroom in the same school, and it's 50%. What do you think's wrong?
Can you say the question again?
Yeah. So we know that it's so in general, we should only we should be expecting to only get exactly 3 people with hyperlipidemia 23% of the time. Correct? But I take it from I do select my population, and I'm noticing that I'm getting the probability, the amount of people with hyperlipidemia is much bigger than this 30% that we expect, right? And that of those 12, I'm actually seeing it at 6. So what should we do? You're getting exactly 6 every time. A better question is, what are the probability of getting 6? Or do you worry about it? We said only 30% of the population, right, should have it. But I'm seeing that I'm getting 6 every time.
Said if 30% of the population have it, but you're getting 6 every time, and that's half of the population.
With the same sample or different?
Let's say I sample 12 children and I see that I got exactly 6.
Then wouldn't you look at other factors that may be influencing that?
Yeah.
You identified something?
They can be dependent.
No, that has nothing to do with that. Remember, you either have it or you don't. That's actually a good thought. I appreciate that. I'm gonna share my screen to show you how we calculate this in R. And the question is better raised to say, so what's happening is, it's called D binomial, and I give it in the notes too. We want to know what's the probability if I sample 12, and the probability of success is 0.3. Okay, so that's how we got the calculation without doing the formula. But what I said is 6. What's the probability of getting 6? That is the question. It's only 8%. That makes me worried, doesn't it? Either my test is wrong, or there's a problem with the children. You can imagine where this occurs a lot. Yeah, go ahead.
It's the children.
Yeah, it's generally the children. Always go with the. I mean, to be honest, you don't want to be invasive to the children. So you do want to check yourself to make sure you test, but typically there's a problem. Something in the environment. Where would we see
The same.
Go ahead.
The same children taking both of the class. I'm saying like the 6 children are taking both of the class. So if you're taking the test from both of the class, they are same.
Yeah, but that could be it. Yeah, if I would readmit the test multiple times to multiple classes in that classroom. So remember, this is 6 to 12. They don't, So I'd be like, okay, I'm doing this, first grade class, second grade class, third grade class, taking 12 from each, and I keep seeing this trend. I'm freaking out.
Yeah.
Now, where does this occur a lot? Asthma.
Mm-hmm.
Why?
Environmental factors, depending on where you are living. You may see it in high prevalence in the city or industrialized area compared to rural areas.
Yeah, or asbestos in classrooms. I mean, if you're specifically looking at the classroom. I mean, taking a sample from a specific classroom.
Yeah. Yeah. I think, you have to think about these confounding factors, right? So you can see where, yes.
So in the situation that you just presented, how did we know the 30% is it a number that was like what the baseline percent is what I'm asking. Was it gathered from everyone and is it the mean average baseline? And then if you take like someone from like a Chicago school, like they may be like an outlier to that baseline. Is that what you're saying?
It could be, yeah, and that's a good point because asthma generally what we do is we base it off of a national level, which is a problem, right? So one of the things I work with is populations in Providence that are immigrant populations. A lot of them have to live in high pollutant areas because they're the most affordable. They're right next to the freeway, the pollutants that come off of the exhaust of cars and semis. We see this in Chicago where a lot of families on the south side live in what's it called? The previous industrial areas, the cleanup areas. What are they called?
Oh gosh.
Help me out. You all should know. This is group knowledge.
Yeah. And I have a friend who works for the lawyer for the EPA, so it's embarrassing. And she worked on one of those sites. It's something sites.
It's a cleanup site or something. But anyways, my point is the reason this binomial distribution is very, very, very helpful is you survey something and you see it's a problem and you say, what's the odds? What's the odds that I'm getting exactly 6 every time? And you're like, oh, crud. It's only about 8% and I'm getting it multiple times. Uh-oh, we have a problem. And you can imagine if you're working with a community where these children have asthma or something like that, or lead poisoning. So people dismiss these binomial distributions, but this is actually quite where it's helpful. Okay. Let me share my screen. So one of the questions would be, another thing is we can say, what's the probability that I'll go 3 to 10? What that means here, I have a total population. What's the probability I'm going to sample 12 individuals and that are positive, the kids will have hyperlipidemia. You'll either have 3, 4, 5, 6, 7, 8, 9, 10, right? So you're summing all the probabilities. One of the things that's important with binomial distributions is patients, you want to make sure the patients aren't related. I think Heba was bringing up a good point. Are you choosing all the same children? Right? Are they related? Maybe all 6 of those children live in the same complex. That's not a problem. That actually tells me a lot of information. Maybe there's a risk factor for hyperlipidemia that we are unaware of. And that's where I call up a medical doctor and say, tell me what is the risk factors? And then maybe we can help support the community to help them navigate and make sure that they get advocacy for their issues. So the mean value for binomial distributions is the number of the population, which here was 12, and the percentage of that event occurring, which is 0.3. So for our last example, again, it's 12 times 0.3, right? Anybody want to do that quickly in their head? It's 3.6, right? 3 divided by 10, 12 divided by 10 is 1.2. Yep, okay. And then the standard deviation for a binomial distribution is given by this formula. All right, density curves. And this is what I think a lot of you have seen and been somewhat comfortable with. So far, we've only discussed discrete probability. It happens or it doesn't. Or that we have a distinct value, right? Rolling a die. But what about continuous? Think height, weight. I think of age a little bit as a continuous. We talked about the difference between continuous and discrete 2 weeks ago. IQ, I hate IQ. IQ is baloney. I almost said a bad word. Thank God my kids are at a baseball game. So they usually represent a continuous probability by a density curve. So it's like a very famous, what's the probability that the population has an IQ between 80 and 120? That says 81% of the population, or about 82% of the population, has that IQ. Again, IQ means nothing, except for extreme values. That's when we worry about it. So let's, our most famous example is a normal distribution, a bell-shaped curve, right? Everybody recall a bell-shaped curve? One of the most common things that we're going to see throughout class, we're going to assume that in general, the population behaves like a bell-shaped curve. Majority of the population's in the middle, and then we have some outliers at the ends. Height is a good example, by the way. So what is this? One of the things that's required is for normal distribution is the mean equals the median equals the mode. It's weird, isn't it? The mode is the most common value. The median is the middle, and the mean is the average, right? But they have to all be the same. The probability of being above the mean or below the mean is 50%. So 50% of the population is above the mean, and 50% of the population is below the mean. So if we said the mean height for women in the United States, I believe is 5'5", 5'4", 5'3". Somebody help me out. I don't remember. I usually have notes. So this is when I'm sick. I apologize. I'm going to keep apologizing. Let's say it's 5'3", okay? What that is saying, 50% of the population is below 5'3", and 50% of the population is above 5'3". Okay, I'm biased. I'm a male. Identify as a male. I will say I know what it is for U.S. men is 5'9" or 5'10". Okay, I lie. I don't know. I used to know. This X value, right, that we see here is what you're measuring. So what this is saying is the probability that what's the probability that you're 6 feet? Okay. Well, we know 50% of the population is above 5'10". So then we want to say, well, can we calculate what's the probability that you will be 6 feet? So what that's saying is how many people are 6 feet and above. So two things I want to recall. What is total probability always? Shout it out.
100%.
100%, yes. The other thing is we're doing we're doing between 2 points. Well, why? Well, you can't do an exact probability on something continuous. Are you exactly 6 feet? You sure you're not 5'11" and 10 inches, or 5'11.2" or something? So let's look at this IQ graph. Probability is given as an area. okay, between 80 and 120. You cannot find, if I want to find area, I need both the base and a height. You cannot find the probability of an exact point. So if somebody says, what's the probability of you being 6 feet? You can't actually say that. You can say, what's the probability? Hi. Hello, guy. So what's the probability of being above 6 feet or below 6 feet? I can answer that. I can't say what the probability of being 6 feet is. This is known as a continuum paradox. Okay. Kind of cool. Paradoxes are great, right? No? You haven't seen enough paradoxes. So the probability of being 6 feet is 0. Because you can't actually calculate it. But I can say what's the percentage or what's the probability of having somebody that's 6 feet or above, or between 5'10" and 6'2". I can answer that. But I can't answer what's the probability of being 6 feet. And this is actually, like, people do this all the time. So we know the probability of throwing a normal die and getting a 4 is 1 out of 6. We know the probability of getting a 2, 3, or 4 is the same as 1/2. But notice there's a difference between these two formulas, aren't there? What do we notice here? What's the difference that we see in the formula?
Equal to or less than, and then less than.
Yeah, that equal sign is carrying a little bit of weight, isn't it?
Mm-hmm.
So here we're saying what's the probability between 2 and 4, but since throwing a die is discrete, right?
Mm-hmm.
It's not like height. So that's why these two are the same. So for a normal distribution, we know that the standard deviation is set. And what that does is basically we wanted to have a bell-shaped curve, and we have some very cool information. And if you've ever taken like the graduate entrance exams, the GRE, there's always a standard deviation example. So let's say the mean is 3.1 and the standard deviation is 0.01. If the data has the behavior of a normal distribution, then what we know is that we can say calculate what 68% of the population will be within some range. So what I'm saying is 68% of the population is within one standard deviation. So if we were saying that the average height of men is 5'10", with the standard deviation is very important, isn't it? Why? Because it tells me how wide or how varied that data is. If the standard deviation is a foot, that's a huge difference between 6 inches, correct? Or 2 inches. So if it's 2 inches, we're saying that 68% of the population is between 5'8" and 6 feet. If it's 6 inches, we're saying that 68% of the population is between 5'4" and 6'4". Oh, yeah, I'm doing the calculation right. That's a big difference, isn't it? Standard deviation really dictates to us what that spread of the data is. Hold on one second. I'm sorry. So for this data, for the example I have here, is we can say the first standard deviation says that 68% of the population is between 3.0 and 3.2. But if that standard deviation was 0.4, it's between 2.7 and 3.5. The standard deviation says how wide we're spread, correct? Under that bell-shaped curve. Is it a fat bell-shaped curve or is it a skinny bell-shaped curve?
Is it flat?
No.
No,
oh,
it's
go ahead.
no, wait. No, it's
No, so,
I'm confusing it for maybe the mean. I don't know. But yeah.
No. What were you thinking, Maricela?
Yeah, I was just thinking it was either oval or round, like how you flat,
Yeah,
right?
the standard deviation will always look like this. You'll always have something like this. But the
Oh,
question is how tight is it or how spread is the data? Or sorry, for a normal distribution will always be this bell-shaped curve.
okay.
Okay. The next, if let's say we're at 2 standard deviations, that says 90% of the data will be within 2 standard deviations. So, for example, it's 2.9 to 3.3. Third standard deviation is 99%. So 99% of the population will be within 3 standard deviations. If we assume the population follows a bell-shaped curve or a normal distribution, we're making a huge assumption that 99% of the data that we've obtained says that the population would fall in this range. Okay. Do you think the average human follows a bell-shaped curve? Let's say about height or weight. Do you think it's really true that height and weight follow a bell-shaped curve?
Professor, I would think so. But
Okay.
there's only so tall or so short a human being could physically be,
Okay.
or there's only so many pounds a human being could physically weigh and still be alive.
Okay. Other thoughts?
I was gonna say no because it's continuous.
Okay. Other thoughts?
I was gonna agree with Kelly and say that there is a mean, or there is like an average height that us humans fall in. So there's always going to be a bell-shaped curve. For outliers, but there are always going to be those mean numbers of averagely what humans height are.
Okay. Okay, cool. I'm not giving an answer yet. That's so mean, isn't it? So one of the things that we can do is we can work backwards. So we know that 95% of the data given should fall in this range, right? So where S here represents the length of the 95%. And we can divide by 4 to actually get the standard deviation. It's kind of a weird thing to do. In the book, table 1 has a table of probabilities for normal distribution. It is not required that you use it. I actually like to use tables personally, even though I have R and Excel and all that. And I can just Google it. It's not a problem either, or use ChatGPT. I still like to actually use tables because it helps me. And one of the reasons we want to do this is, in that example I've given was about IQ, right? And they say the average IQ should be 100, and the first standard deviation should be between, the standard deviation should be 20. The problem is that's not in what we call standard normal distribution. And what we have to do is we want to convert it to do a lot of calculation to what's called a standard normal distribution. And we call it the Z distribution. And what we do is we say, we're going to take X, subtract the actual mean and divide by standard deviation. So if we do example number 10 in the book on page 99, what we have is diastolic blood pressure are assumed to follow a normal distribution with a mean of 85 and a standard deviation of 12. Right? So let's, before we jump into this, we're assuming a bell-shaped curve. Cool?
Mm-hmm.
Not only that, what we're saying is we have a mean of 85. So on average, a person should have a diastolic blood pressure of 85. By the way, diastolic is that second number that you get, just so you know. And the standard deviation says that 68% of the population should be between 73 and 97. I don't know if that's true, by the way. And I'm curious where they got this data from. What was the population set? So one of the things is what we want to do is what portion of the population has a diastolic blood pressure less than 90? So from the table, we can calculate that 90 minus 85 over 12 gives us 0.42. And then we look in the table backwards to find what the probability value is. So from the table, you're going to get 0.6628. And again, if you're having problems using the table, please come talk to me. So what this is saying is that the probability that the diastolic blood pressure will be less than 90 is 66%. If you want to do it in R, it's actually quite easy. You say, what's the probability? Get a 90, we have a mean and a standard deviation. Okay. So it's very, in R, it's very simple. I don't even have to find the Z value or use a table. And the formula in Excel is pretty similar. Next, what's the portion that has a diastolic blood pressure between 80 and 90? So what you want to do is we want to calculate that P norm between the two and find the difference. Okay, it's 32%. What if you go to the doctor's office and you're like, I'm getting a diastolic blood pressure of 100? Right? Well, the question is, what percentile am I in? Also, what are you worried about? Don't worry about calculating. What do you worry about if you see diastolic blood pressure of 100?
What is the likelihood that I'm going to die?
Yeah, it's pretty high, right? Either you have high blood pressure, or you're in shock, or you're something else, right? We're not medical. Well, I don't know if any of you are medical doctors, but I'm not. And so, but I see something like that, I'd worry. But we can calculate this in R, and let's see. I didn't put it here. Sorry. So yeah, we do have some concerns. All right. We're going to go into discussion here in a second, but I want to talk about this. Assume the distribution of a population can be normal or non-normal. Taking a simple random samples of size n from a population with replacement. Then for a large sample size, so it means our sample size is bigger than 30, the sampling distribution of the sample mean is approximately normal. This is huge. So if my sample size is bigger than 30, I can assume that my sample mean will follow a normal distribution. 30 is not big, is it? I don't think of 30. Yeah, you can. That's huge. you don't even have to sample a large population. This is why they get away with, certain type of survey questions. So the way it works is the mean for our for the population is equal to the approximately to the mean of the whole. No, we'll just shoot me. Sorry, hold on. You don't want to hear this. Sorry. And the standard deviation is equivalent to the standard error. We'll come back to this more, and it will come up quite a bit for us. So let's do problem number 11 from page 99. And I'm doing problems from the book, partly because I realized 2 weeks ago I wasn't using problems from the book, and I was enough to help you figure out how to do it for your work, for your assignment. So I apologize for that. So here we're going to consider the same population that was described in problem 10, where we have that diastolic blood pressure. We're going to say if 15 participants are sampled, what is the probability that their mean diastolic blood pressure exceeds 90? We can use the central limit theorem since in 10, we assume the population was normally distributed. Notice, since we assume a population is normally distributed, it doesn't matter if our n is bigger than 30, okay? But if we do not know if our population is normally distributed or whatever we're trying to measure, then we have to have a large sample size. So the mean for those 15 will be 85, but our standard deviation is really going to be 3.10. So what this allows us for is that a little bit more variation, right? And look at it, it's scaled based on how many people that we sampled, right? How many? So here we're scaled by 15. So we want to know what is the probability that their mean diastolic blood pressure exceeds 90. So we want to find out what's the probability of being up to 90. That's what this P norm does. We're going to do 1 minus that calculation. Okay. So if we're above, it's 1 minus. If we're below, it's just a value. All right. So we're going to pause here. We're not going to pause, but what we're going to talk about here is I want you to talk about the paper. Okay. So in the paper, you're going to go into your breakout rooms again. And I would like for you to have a conversation about what type of information was presented in the paper, what was presented well, what wasn't presented well, what you understood and what you didn't understand. And this time I'm going to give you 10 minutes. And again, find a reporter for your group to discuss to discuss what do you think the key takeaways of the paper should be. Okay. So if you had to summarize this paper for somebody that's not in this course, what would you have to say about it? Okay. So let's do our breakout rooms. And you're going to be, the rooms will be a little bit different.
Who wants to share our thoughts with the main group?
Do you think I think you might be the most fluent speaker, Chelsea.
I don't mind, but I am totally other people should do it. I mean, you get as part of your participation group, so I mean, grade, but I can absolutely do it. So it'll be me, Usman. What do you think?
Yes, I think you're the most.
It helps to be a chatty Kathy, I guess. Okay. I love the map in this. I don't like charts. The first thing is like the second table in this paper. It was just, oh, I didn't even look at it. I mean, I just glanced at it and was just like, ugh. I really, really love the neighborhood map with the zip codes. It was really interesting to me because it really clearly.
Have you taken a GIS course? Because they actually teach you how to make those maps. Geographic Information Systems. You can pull information off of CDC Wonder and then add it to the map data and then sort it out, color code it, and just like the zip code.
Yeah.
And it just formed the boundaries, and then you have different overlays on the map, and you actually can make the map, which is used in pretty much every textbook you have ever purchased. Probably.
Yeah, and it's geographic. What does it stand for?
Geographic Information Systems, GIS. I took that at NIU. I think they finally started a class. Dr. Bannis started one class in the public health. Yeah, I think it's an elective.
Yeah. I'm going over the conclusion again.
Yes, I'm reading the conclusion again also. Were you guys all able to work remotely during COVID? Yes, I was at NIU finishing my bachelor's degree.
Yeah, yeah.
Time.
Because I'm reading like one of the reasons maybe the higher incidence rates of COVID in these neighborhoods are work environments, and it's just interesting. I was able to go completely remote. A little towards the end, it was kind of terrifying because I live alone.
Yeah.
Oh.
Yeah.
Yeah, it would be mostly hospitality workers and factory workers.
Yeah.
Are the two where you can't work remotely.
And factory workers. I'm going back up to that map. I love this map.
And I'm more familiar with the suburbs, but these are all the zip codes within Chicago.
Yeah.
Yeah, I know Bensonville has a lot of factories outside of Chicago. But there's a huge cluster west side of Chicago.
Yeah.
It looks like that's where UIC is, which is the medical center, and Rush Medical Center. So
that's a
Yeah,
That
I
is,
think it's 60639 and
mhm.
60647. So
Well,
that's where the hospitals are.
60647 is Logan Square.
Oh, okay, okay.
But no, you're
Oh, maybe it's 60622.
yeah.
That could be the one.
Definitely.
Okay.
That's Ukrainian village. That
Uzman,
is,
you were gonna
Which
say
is the
something?
middle of those four.
yes.
Uzman, you were gonna say something?
No, I was just coughing. I'm sorry.
No, please contribute. Alexis.
Mm,
I mean, let them know what was your guys' thoughts on the paper. Uzman, Alexis?
Uh, I'm so sorry I didn't get a chance to read the paper. I'm so sorry about that. So
No,
No.
being honest is much better than trying to fake it. Trust me, it's not a
Yeah.
problem. But look at it now and hear what they're saying. Look, ask them
Mhm.
where they're looking at in the paper.
yeah.
How about Alexis?
Is there a way to share screens in this with Zoom?
I think you can. I think I opened it. You
Oh,
should be able to.
yes, I can. I'm going to share my screen.
Yeah, you're doing it. You're doing the good stuff.
Yeah.
Oh no, I can't. I can't. Host disabled participant sharing. Okay.
Okay.
Now try.
I love it. You guys are gonna love this map. Okay.
Oh.
Do you all see this map of all the zip codes?
Okay.
And what Ananth was, I'm sorry, Ananth.
Yeah.
He was saying like 60622 and 60612, like right here is where the medical centers are, like Stroger and Rush and things that may
UIC, yeah.
Yeah, and UIC that may be influencing numbers there. So I think like this area is Formosa, this is Logan Square, Humboldt Park, Ukrainian Village, Edgewater, Rogers Park area up here.
I think 60645 is Washington Park area, and they have the trauma center.
Oh.
University of Chicago Trauma Center.
Where's
so that's another
60645?
It's in the south. There's a cluster 60615.
Oh yeah. That's interesting.
So that's another hospital.
Mm-hmm.
For the others, I think they're neighborhoods.
Mm-hmm.
So the biggest clusters are the hospital districts.
Yeah.
All the other clusters are the neighborhoods
Mm-hmm.
where you might have more hospitality workers and factory workers living.
Yeah. And in this area in the middle, there's a lot of high Latino population, which I remember that was a higher incidence rate. Anyway, there was this other table too, which I can't make heads or tails of.
All right, 5 seconds. See you in the main room.
Okay, see you.
All right. Welcome back, everyone. All right. Ivory, Kelly, Tiara, and Zubia. Who's your spokesperson?
I think Kelly did a great job, and Zubia.
Oh yeah.
Yeah, I'll be glad to speak. We generally agreed that the survey did a good, or we generally agreed that they did a good job of explaining or proving what we kind of already knew. And they were able to illustrate that there were differences in comparison between zip codes. They tried to explain or explore the differences between adjoining zip codes and why one would be more affected by COVID than the adjoining zip code. Was it something to do with a number of different factors like race, income, and as it turns out, the study itself found that the zip codes did interact more, but people with different levels of access to care based on race or income had different outcomes, and they were able to demonstrate that through proof.
Thanks, Kelly. That was great. All right, group 2, Bonita, Iba, Marisela, and Zahara.
Okay, so we had several findings or several things that we actually picked on. So going to the tables, one of the things that we talked about was the representation of data, just at a numbers point of view. Table 1, for example, does a really good job breaking down the different categories for those who were affected by COVID based on the age, the gender, race, ethnicity. One of the things that I did point out was I thought it maybe would have made it a little bit simplistic as a follow-up to table 1 to represent this data on maybe a histogram or something like that, so we can kind of do a compare and contrast analysis, and you can actually have a visual in front of you. And then as far as table 2 goes, actually, no, I'm sorry. I'll jump over to what the map looks like. So as far as what the map looks like, one of the things that we talked about is that we noticed there is a cluster, and I think the first group just sort of like touched on that a little bit, and how the numbers that clustered around each other, I believe is zip code 603, 60639, 60647, 60622, 60612, how there was a good mix of detectable and undetectable, I guess, strains of the SARS, so the COVID-19. That was also, but then, it was in clusters. So there is maybe a little bit further research that maybe needs to be done on that. I know obviously there are other factors that were discussed in the article. There are certain social determinants of health that might have affected certain areas more than others. I know did we talk about income level? Okay, so there, those who were insured, those under a certain poverty level, and other factors that sort of got into play. And one of my group members also talked about a limitation to the study, and it is our Marisela. I'm sorry, I forgot what that was. Was that a population that we pulled from? Is that what the limitation was?
Yes, I believe so.
Okay.
The limitation, like the way they have recruited the people for the testing.
Yes.
Yeah. Good point. I didn't even catch that when I read it, to be honest. It's usually one of the things I'm always looking for, and I didn't catch that. That's good. All right. Group 3, Ananth, Chelsea, and Usman.
Yes, and I'll be speaking for the group. I think we really spent some time looking at the map, and I was able to share my screen. Thank you. Really like.
Yeah, by the way, when you're in your breakout rooms, you can share your own screens.
Yeah.
So you know.
That was kind of awesome because we were able to look at the map together. And Ananth really pointed out like some of the clusters, maybe because it's medical centers, that might be a possible explanation for it. It was very interesting, and I was thinking like what I thought about was the work environments and how many of us were able to work remotely versus those who were not able to work remotely. And then it was brought up like because I think obviously the service industry, but people are all, as someone brought up, people working in factories and such. And I was like, oh yeah, that's like a closed environment. You can't call out sick, you know? So, like, yeah, that would seem to be a major factor. I love this map. And then, I guess there is such a thing called GIS, which is Geographic Information System. That was pointed out to me. I think it's an elective class maybe coming up.
It is an elective class, and I highly recommend it for anybody that's interested in working for the government.
Yeah.
And loves these type of maps because this is generated probably using ArcGIS. You're taking it. Yay, Marisol.
That's awesome. Like, just for my work, like I was like, oh my gosh, I would get hugest raise if I could like do this in our service area, and how many people, you know, I was just like, this is super exciting that there's this information out there that we are able to learn about. Anyway, that's our group.
Awesome. Thank you everybody for sharing. I know we're all getting tired. I have about 15 minutes left of notes. Usually we take a break by now, but do you guys want to push through? Because I know I'm exhausted.
Let's just push through.
Oh yeah, for the GIS, if somebody wants to put in the chat what the name of that course is, since Marisol is taking it. But we do give a GIS certification at NEIU too. So we have a lot of people that'll come back. Hi. It's stop. Hi. I love it when we see our families, right? Either little fur balls or...
Oh, there's a little bug over there. Hi.
So hi. All right. So it makes me happy when I'm not feeling good. Thank you. All right. So what we're going to talk about next is confidence intervals. And we're just kind of doing a little introduction to it. Here, we'll continue to do it further next time we meet. But so to do confidence intervals, basically we're saying we do a survey, or I get this data from a population, and we say we have a 90% confidence that the data lies within this range, or 95% confidence the data lies within a range. The way to do this and to do these calculations is very, very, very dependent on the type of data. So if we have one sample, let's say we're drawing people's blood, right? And there's 50 of them, and we want to check our blood pressure. And what we're looking at here is that'd be continuous. And we're going to be estimating what is the mean. So the average of these 50 people that we got the blood pressure for, we say that 90% that we're confident that the population's mean would be within this range, right? Remember, what you're doing is you're taking sample and trying to predict what it would be for the whole population. Taking samples, trying to predict for the whole population. That's the key here. You cannot sample the whole population. Now, let's say we're taking 2 independent samples, right? So blood pressure and a lot of things depend on blood pressure. So let's say oh man, I am blanking. But two values from an individual that are independent on each other. Yeah, a lot of it's related to weight, and that's the problem. Blood pressure is independent on weight as well. So, sorry, I'll think of one. And there, what you're looking for is the difference in means. Oh, yay, Eva, that's great. Blood pressure and hypolipidemia, they are not related. I don't know. I'm assuming they're not. And so what we're looking for is what's the difference of the means. Two dependent values, blood pressure and weight. So there we're looking at the mean difference. And then finally we have dichotomous, right? So if 30% of the population let's say actually sorry, I'm getting tired of my brain fog. But we have dichotomous, remember, is that binary, basically. You're one or the other. Dichotomous is two. Okay. So this is more that binomial distribution. And here again, it's one value that we're measuring. And here's two independent. Notice you don't have two dependent. It's way beyond the level of this course. You would see that in a graduate course in mathematics. Okay. I personally don't even know how to calculate it. I have to look it up like big time. And I had to do it once and I've forgotten, but it took me a month. So it's not the point of this course. These are the 5 that we normally see. I just want you to know you're looking at mean, difference in mean difference, proportion, different in proportions. Remember, a proportion is a percentage basically. Okay. By the way, I use this table all the time. I actually go back to my slides that have this table when I'm trying to do statistics. I just got a review back from a paper, and they're like, well, you guys should have done an ANOVA test. I'm like, no, that's wrong. That's a wrong test. And I pull up my ANOVA slides for my other stats course I teach. I'm like, this is why. And here's a reference. You do not use ANOVA for this type of data. Same thing here. Confidence interval, what type of data are you working with? So my question for you, where do you see confidence intervals in your daily life? I'll give you a big hint. Something's very important happening in about a month.
The election?
What do you keep seeing all the time on the newspapers and on the news and social media?
So is that what they call the margin of error?
It is. It's related to the margin of error.
Okay.
So when we think about a confidence interval, we can think about that margin of error. In particular, the word means what it is. How confident are we that the population would be within this interval? The mean of the population or the proportion of the population would be in this interval. How confident are we that the whole population would fall within this range? Do you think people know what a confidence interval is in general? Chelsea, you shake your head no. Why?
I don't think so.
Why do you think that's a problem?
I think people like to think in absolutes. There's comfort in that, and this is a little bit scary because it's a bit of an unknown. And you can present data as like this is the truth, and there's a good chance it's not. It's just an interpretation.
Yeah, and we have to be careful, right? I agree with you 100%, and I think it's important that we're very clear that we're just saying we're 95% sure that the whole population would fall within this region. We could be wrong. 95% means 5%. I could be wrong. That's okay. As long as we're honest with ourselves. Bless you. So how do we calculate this? So what I'm doing is I'm kind of giving you a general formula. So we need the sample size. We need the sample mean, need the sample standard deviation, and the confidence interval that we usually want is 95%. That's pretty standard by National Institutes of Health, CDC, and WHO, World Health Organization. These are very standard across the board. There are times that we want it to be higher at 99%. Typically, you don't want it to be lower. So 95% is the gold standard. If the distribution, if the amount of our sample is bigger than 30, we assume a normal distribution, right? Then we say we could do that. And this is our formula. So we have that Z value. If it's less than 30, we do what's called the T distribution. It used to be called the student distribution. And that's what this T is. But the formula is the same. Anybody seen this plus or minus? It means plus and minus from the value. Add it and subtract it. From table 2, we have what's known as this T distribution. We have this thing called the degree of freedom, which is n minus 1. And basically, what we're saying is n is how many samples we have. Let's say we have 20 samples of people's blood pressure. And what we're going to do is we're going to say that our degree of freedom is n minus 1, because what we're doing is we're holding one value and then we're placing everything around it. So that's why it's called the degree of freedom. So this is what those graphs look like. So the Z, or that standard normal distribution, has that bell-shaped curve. As n gets closer to 30, it becomes more like that blue curve that we see here. And if n is really small, it has this big wide curve. So problem 1 from chapter 6, let's say we want to calculate it in 95% confidence interval for this following data. My question to you is, are we using a normal distribution or a T distribution, and why?
T distribution. Because it's less than 30.
Exactly. So since we want to do that, what is the degrees of freedom? We'll go back. What's our sample size?
Nine.
So our degrees of freedom are, here, I'll help us out.
8.
8, yeah, good job.
How did you get that? I'm sorry.
Yeah, Benita, how did you get that?
I just applied the formula n minus 1, which should be n or sample 9 and minus 1.
Thank you.
Oh, by the way, just so you all know, starting the next time we meet, I'll be providing the slides ahead of time. So you can write on the slides a little bit more detail. I didn't do it before because it wasn't necessary, but now we're getting to the point where we're doing calculations and you're going to want to play with it a little bit.
Yeah.
Okay. Sound good?
Yes, thank you.
Okay. So we have to use the table. So the degree of freedom is 8. From the table, we get a T value of 2.306. So the mean was 196.11. The T value is 2.306. The standard deviation was at 29, and n is 9. So just kind of do it. And we represent it in this open interval. Okay? And so what it's saying is our values are between the left and the right. Okay, so what we're saying is we have a 95% confidence that our data, the whole population, would fall within this range.
Okay.
We are I'm gonna repeat it. We are 95% confident that the population would fall within this range. It's very important. We have a 95% confidence that the mean would fall between this value. And this is how I write it. It's probably better to say population mean, but it's just, this is standard is mean.
Okay.
We will
Question.
next time. Yeah, please, Bonita.
Okay. Do we always report our confidence in 95 percentile, or would you want us to maybe specifically report it in whatever, I think there's 90 as well.
So there's 90, 99%, 90, 95, and 99. And even sometimes 85. Do for the homework, you'll do what the question's asking. Typically, if you're unsure, 95.
Okay.
And by the way, there's a big push from NIH to shift everything to 99%.
99%?
Mm-hmm.
How accurate? Okay.
So
I
the
guess we
range
should
would be
probably get
wider.
that. Okay.
Yeah. So the values are going to be larger, or the range of the values. All right, that's it. Next time we'll start with confidence intervals some more. I just wanted to give a flavor. But factorials, I have a little side for those that want to understand what those are. I love it. What can I say? All right, questions. I'm sorry for ending class a little early, but I'm starting to lose my ability. It's taking a lot of energy right now to talk.
No,
I
don't
have,
worry.
sorry, I have more of a concern and that I could address with you after class is over.
Okay, yes, that is totally fine. By the way, please, if you're struggling with anything, come to those extra times on Thursday. I think it's really, really helpful. Like if you're having struggles with the technology side, we really can spend time helping each other out. And what I meant by we is like, oh, I don't know. And somebody's like, oh, I did this. This is how I did it. And I'm there. I've dedicated myself to be there on the times that we're not meeting. Okay. And then come to the office hours as well, either the virtual or the in-person, if you have the ability to, or if you need a schedule outside of those times, I will try to find a way to do that. Other questions?
No, but I had needed to let you know something.
Okay. Is it personal?
I mean, I'll mad sharing with everybody, but it's not that.
Okay. Well, why don't we wait for people to let people go or ask their questions, and then we can start with you, Tiara, and then we'll go to Benita. Is it okay?
Oh, that's fine.
Okay. All right. Just so you all know, next week is October 3rd. We are not meeting, but you'll have a discussion post about your project, and it's going to be asked for you to post a paper related to your project. And just give us a summary, which you're already doing, right? You already have a paper. You probably could do this like that. And then obviously respond to your peers. During that time that we normally meet in person, I'm in BBH. Please come by. And if you need to meet virtually, I'll do the best I can with virtual too. Okay.
Oh, sorry. I have one question before you let the class go. So I know the discussions, there's obviously shared so everyone can kind of like jump in, see what you posted and chime in and give you some feedback. But the project, I know that actually is not shared. Would you be okay if we sort of like bounce some ideas off of each other or kind of like worked with somebody else that maybe is working on a similar topic or idea or something like that?
Yeah, I want to make sure that you're presenting different data,
right?
But they can be related. For example, I know Hiba, you're looking at oral health, and who else was also looking at?
Me, I am.
Oh yeah, you have similar topics. You can share some information back and forth. Hey, I found this paper; it would be helpful for you. Or let's talk about what are the issues? Are we finding the right data?
Okay.
Yeah. That's a great question. Thank you for asking. But I do want them to be significantly different in some sense.
Okay.
Okay. Yeah, that's a great question. But yeah, help each other out.
And Hiba, don't be bugged out by me. I sent you a message. Sorry.
Is the paper and presentation due this exact same day?
The first presentation is October 10th, and the paper is due there then as well. Yes, you don't have homework due that week. Okay. Cool.
It says we're gonna upload a recording. Is that, are we presenting in class or are we recording ourselves?
No, so what I'm gonna actually probably have you guys do is, since there's too many of us to present over 3 hours, isn't there?
Mm-hmm.
Do you all want to sit here for 4 hours? From 6 to 10? No. So this is what you're gonna do, and I'm gonna post this online on D2L to the front page of our course. But I'm gonna let you know, because Anant was asking me about this as well for more details, and I had to really think about it. You're gonna post the full presentation, that all the expectations. In class, you're gonna get 3 minutes to present only 3 slides. Only 3 slides. To just give me an elevator pitch of what was the question? What has been done? And this is one interesting graph or data table I wanted to share. 3 minutes is quick, and I will cut you off. No mercy. But does that answer your question, Ivory?
Yes.
Yeah, so they're both due the same day, but you'll have the slides already. Zahara.
Yes, so when it says the portion of presentation of data, so we can gather data from all of our resources that we've gathered like on our topic and present that data.
Yeah, but remember, you have a limited amount of time for your recording and for us in person, correct?
Mm-hmm.
Right. So
Yeah,
3 minutes, a minute for each slide.
Pretty much, yeah.
Okay.
But the recording can be longer. But remember, there's in the project, it's very detailed of what the expectations are. Yeah, good question. Other questions? Next week is a good time to come see me. Please take advantage of it. All right. Good night, everyone. I hope you all feel much better than I do.
Good night, everybody.
All right. Tiara and Bonita.
Good night.
Stay on.
All right. Good night, everyone.